Did somebody else start the recording?
Yes, I did, so that's
Okay.
Okay. First of all, thank you for coming to this technical sharing. And today the topic is not trying to explore some technique or something in depth. I just want to share one way of thinking, one idea, or one something I think it's interesting. We can put it into our memory, in our system design. And to be honest, I think FPGA is right now is quite popular in the industry, and maybe we can find some clients who may be interested in this kind of implementation. So this presentation is trying to explain some terminology, explain something common, or and I want to focus on how to integrate FPGA, not to develop FPGA, because most of us are embedded software engineer, and I think we have some colleagues who are who are quite professional on FPGA development, but personally I'm not. But I think know how to use it is also helpful to my daily work. So let's start. I want to emphasize the possibility. What does possibility mean? Because in every design, we can eventually meet the requirement, but whether it's a better design, we're not sure unless we know a lot of options, a lot of tools, a lot of techniques that we can use, so we can achieve a better possibility, especially in system design. So about the contents, first section is to explain what this presentation trying to explain, and the second section is to discuss exactly, use some examples to show, to demonstrate the possibility, especially better possibility FPGA can bring to embedded Linux. And in the third one, I will use some example coding to show how it works. And the fourth section is about how to work better. I mean, better is not about performance or functionality. It's about the working flow, because most of embedded developers may or may not have enough knowledge or skills to work on FPGA development daily work. And the same is to FPGA developers. So a better, I mean, it's not better, but a clear, a decoupled working flow so the two teams, Linux teams and FPGA teams, can cooperate better, smoother. And in the end, I want to share some extra things that I think is happening in the industry, and it's quite interesting. So let's start. What this slide is about. So I don't want to try to cover any hardware descriptive language syntax, or how to write the Verilog of VHDL code. To be honest, I'm not skilled enough to explain that topic, but I want to compare FPGA to Linux system as something milk to our body. I mean, first of all, is milk good for our health? I think the answer is positive in some cases. So I want to drink it. Then I want to know what kind of factors I need to consider when I trying to drink or buy a bottle of milk. And actually, I don't care about how to write FPGA code. That's not my business. And my way of thinking to understand FPGA is, as you can see, they have their HDL language, and they have their synthesis implement procedures to generate the schematic, to generate something like the PCB. But I only care about their outcome is a binary file. The binary file is to instate the FPGA device into a specific circuit. That's a very easy understanding, but actually it's just a facade of the reality. I mean, the reality is much more complex than that. But generally speaking, it's a binary file, and if you load that binary file into the FPGA device, it's kind of a circuit instance. That is a milk, and I need some bottle to contain the milk. That is a hardware description. It may vary in different forms. Depends on the vendor, depends on their tool chains, but the essence is they need to provide some information that so the software, Linux software, can use it. For example, the registers, something like that. So I mean, basically, I just want to focus on how to get the binary file, how to get the hardware description. Then let's talk about why this FPGA is useful in some cases, and compare with other alternatives like ASIC, like NPU, like general purpose CPU. First thing it brings is about performance improvements. One very easy example I made here. It's just an easy example. If we, for example, if we want the Linux embedded system to handle network traffic, layer 2 Ethernet traffic faster, how can we do? Common practice is to offload the data plane into the hardware. That's what they do in the DPU and NPU and many other network devices. If you want to achieve, for example, 25 gigabits or 100 gigabits, that's that's overwhelming traffic to general purpose CPU. In this example, we keep the control plane that is a forward database still in the Linux system, in the software, but we put a copy or a mirror into the FPGA device, into the hardware. So the data plane normally will not generate any interrupt from the Ethernet device to the Linux system. That means the Linux system don't need to handle any interrupts on the data plane. Instead, hardware can learn the FDB from the packet, from the frames, and look up the FDB and do the forwarding work for the software. And actually, the same thing applies to ARP table, to layer 3, and routing table, and then even NAT table, network address translation. It's actually a very common practice. I don't have I don't have the exact figure about the performance improvements, but I can remember I mean, this kind of design can easily achieve the a full line speed compared to general purpose CPU. So that's about performance improvement, and also about functionalities. Here I provide a case. It's a fake case. For example, one customer wants to implement a device, and the device is trying to control another under testing devices in their lab, and so developers and users can remotely control the devices and integrate into the testing loop. So they want to connect one serial UART connection to the device and use some GPIO and electric design to power on and power off the device and select the boot mode, something like that, and provide internet connection. Of course, you can use some mini PC and buy some gadgets and try to integrate. And but one alternative is to use an FPGA, and inside the FPGA you can just create a lot of blocks of serial controller, of GPIO controller, and Ethernet controller, and that's much easier, and you can implement, you can reload the FPGA device into any types of peripheral devices with given resources. I mean, FPGA hardware resources like lookup table, flip flop, that kind of thing. So basically, it means flexibility on functionalities, and also when we combine functionality and the performance together, and sometimes it's the only choice. I mean, sometimes, for example, in the radio base station, when the data unit want to connect with the radio unit, they need a very high bandwidth, much higher than the traffic it tries to carry, because due to the digital signal processing procedure. So it's quite common to find like 25 gigabits with 16 ports, and the protocol stack is kind of customized, and in this case, the user wants to support various type of protocol stacks on one device. I mean, if you want to, and also taking the bandwidth into consideration, it's extremely hard for general purpose CPU to handle this case. And one very interesting thing is, especially in network traffic processing, you can easily buy some IP from like Intel, Xilinx, and any other vendors, and they can provide actually the protocol stack by the form of IP block. You can just use it like you are using a library in software. It's quite it's quite easy, and it's quite easy to meet the functionality requirement and the performance requirement at the same time. And so compare FPGA to other alternatives. If compare with CPU, it can provide it brings possibility about better performance and more flexible peripheral and hardware. Compared to ASIC, I think ASIC is specific, application specific circuits, but FPGA is kind of general specific. I mean, general specific means it's not one FPGA device is not targeting at one specific application. It can be reconfigured to any specific application. And also, it's FPGA normally is cheaper, especially when you're not trying to produce massive amount of productions, like small quantity, hundreds, thousands, yeah. Because if you want to utilize ASIC, you have to pay extra costs about the production and the design, yeah. And also it's quicker because ASIC need the hardware production costs more time, and if you use FPGA, you just need one FPGA device. It's so it can the time need to launch your product to the market is shorter. And compare FPGA with network processing unit and data processing unit, is that FPGA can be used in any application, but NPU, as its name suggests, is for network trafficking. So I want to conclude here. So FPGA may be useful. It may be a better possibility in some design. It depends on the requirement. Okay, how it works. Here I use Xilinx Zinc 7000 as an example. This device, I think, is quite popular because Xilinx has a very good ecosystem. They provide a lot of things, but I have to say their toolchain is sometimes is changing too fast, and sometimes a lot of problems that you have to bear. Yeah, here I have a device here. I don't know whether you can see it. It's this tiny board. It has 7000 on it, and yeah. The requirement I made here is I want to create a vault, which means when the user trying to access a region of memory, they need to provide the password first. So I want to protect one memory area by a password. Normally, I think it's not that easy to do to implement it on the Linux system, but we can easily do it if we have customized hardware, customized like memory controller. And I want to say that this design is not safe at all. It has a lot of problems and very silly problems, but it can be used as an example to understand the working flow. So regarding FPGA side, FPGA developers need to write their hardware description language code, and they need to do the procedures including synthesis, implement, simulation, yeah, many things. And finally, eventually, they will generate a binary file and some form of hardware description. So let's see how we can do it, pretending we are FPGA developer. Okay, here I created a block for the zinc processing system that is a ARM core, and use some basic reset system, Axibus smart connection, and implement a customized hardware device. And this device can be memory mapped to the ARM core, and yeah, I can where is it? Sorry, here. Yeah, here. Yeah. So here. So here I hard coded one password, and the user have to write this password into one memory address, and only after that he can access the memory. If I don't want to explain the very long code, it's not our interest. So yeah, after the blocking design, I need to run the synthesis implementation and eventually generate the bit stream. And also I need to export the hardware description information. And in Xilinx toolchain, maybe years ago, they have a format called HDF, and now they switch to a newer one, XSA. But anyway, it's just a file format that contains all this information, like address map and many other informations. But we don't need to care about if we are using Zinc, because every vendor they are supposed to provide the toolchain who can use the file they exported, right? So we don't need to care about it too much, but we just need to know after FPGA developers work, they have a binary file, they have a hardware description in some file format. And okay, after I get these two information, we can start the Linux work. So given the hardware description, that means the board or part of the board is known from the perspective of Linux software, then we are able to create the BSP. Of course, we need to use the toolchain provided by the vendors, and then we can create the Peta Linux project and create the first stage bootloader, U-boot, and also the Yocto project. And after this, finally, we come to the area that we are most comfortable with, that is a pure Linux software development. And in this process, FPGA, we can treat it just as a firmware binary. So we can, I want to show, yeah, this is what I did last night, and I get here the XSA is a file format of the hardware description. We need to get parse this information, and then we can configure like rootfs, like U-boot, like FSBL, like Linux kernel, and then we can package. We can build the project and the package what we need. For example, here I packaged the first stage bootloader, the FPGA binary, the U-boot image. And here is because I want to boot from the SD card, so I need to kind of create some kind of partition. That's but that's not something important. That's just some practical thing. So basically, as you can see here, we didn't care too much about FPGA's implementation. We just need to use this one, the hardware description, and we just need to kind of package the FPGA produced binary file. That's easy. And then let's see how it works. Here, let me check. Oh, here. This. Map. Yep. Oh, sorry. Yeah. Right now this area is 0, and it reads arrow, but it doesn't mean that the memory is actually 0. I can write something into it, like oh no, read it again. It's still 0, and now I will provide the password. Let's see what happened. Yeah, as you can see, now we can access this area, this region of memory, and then I clear this password, like close the door, and read it again. Yeah, we cannot read it anymore. So that means the FPGA the FPGA logic is actually working. And I remember last time Mahnin mentioned one client want to use some kind of how should I say, shadowed memory, user write something into the memory, and there is also one shadow area stored exactly the same copy, and when they read it, there will be a check whether the shadow area matches with the memory that is writing to. I mean, something like this can be, if they want, they can implement, they can create a specific memory controller. And if you want this kind of device be agnostic to the monoc, free, that kind of system call. Yeah, you can also create a like shadowed DDR memory controller, but that's very complex, I should say. But at least we know it's a possibility. We can do like that, right? It's just complex. So, yeah. To summarize this section, I just want to say, I mean, as a Linux developer, we need to, if we want to integrate FPGA into our system, we need to request at least two things from the FPGA developers. That is the FPGA binary and the hardware description. After that, we can work. Of course, some other things like document. Okay. I mean, in practice, Zinc, no matter it's 7000 or ultra scale or ultra scale plus, normally developers are complaining about their working flow because they are combining Linux development or maybe FreeRTOS or bare metal. I mean software. They are mixing software development with hardware development, and they're. I mean, in reality, it's a barrier. It's a knowledge barrier or skill set barrier between FPGA team and the software team. So I heard a lot of times developers complaining about using toolchains or designing system in Zinc. So I think in practice it's extremely vital to decouple, especially the working flow of software design and FPGA design. We need to be extremely cautious to don't mix them. It brings a lot of trouble. For example, one thing is, building or do the simulation of FPGA design takes a lot of time, like one night or one day to run a full round of simulation. I mean, if the FPGA building or FPGA jobs in the CI system is the upstream of Linux release, it's a catastrophe, right? You don't want to wait one day for one of your upstream, right? And another thing is normally Linux software, especially application level, iterate much faster than FPGAs. So you when you want to do one release of your product, and you don't want to wait like 2 weeks, 3 weeks, 1 month until your FPGA colleagues finished their design. It's also horrible. And so decouple means everything in the working flow. Some suggestions or some practical tricks about how to eliminate or avoid dependency from FPGA to Linux. One thing is you should never introduce the dependency of FPGA binary in your Pattern Linux project, except for the rootfs. So here is a bad example. I packed the FPGA binary in my boot bin. So that means if I want to boot the U-boot Linux FSPL, I need to get the newest or latest FPGA binary. That's hilarious, right? we just cannot do that. So you'd better use the binary just as a firmware, like how we're dealing with what Bluetooth device or Wi-Fi device. You have a binary file in the open firmware directory, and you can load it when you need it. And so the firmware is broken does not cause your Linux system to crash, or or the boot process to fail. So decouple from the building time. And also, we should try to avoid any unnecessary change to the hardware description file. And I can explain it in more detail later. But the idea is we need to, when we do the design, we need to take care. We need to think about how fast or how frequent the hardware description can change. I mean, for Linux developer, we don't want it to change forever, because every time the hardware description changes, you need to reconfigure your Linux project. And in many cases, if you don't do that, nothing wrong will happen. But but you are betting on your lucky. I mean, the toolchain from the vendors requires that. That's simple. And so here, if the FPGA changed their implementation, that means in many cases it means the peripheral devices or the hardware design seen from the CPU also changed. I want to say it. So FPGA changes in FPGA development means changes in hardware. So seeing from the CPU, that means peripheral devices attached on the Axi bus changed. So if we never change the hardware description, how is that possible? I mean, the hardware actually changed, but the description file didn't change. So there is a mismatch. So how we solve this problem? In practice, people are using device tree overlay. So I provided the link here. It's a kernel document. If you're interested in that, you can read it later. Basically, it means there is one device tree. There is a living device tree in Linux. So we can and it is passed from the U-boot to the Linux. But Linux provided one mechanism to trim the change or add some leaf, trim some leaf, trim some branch from the tree at runtime. So that means the probing, the probe of or the matching of device and driver can happen at any time that you choose. So you have the driver, loaded, and but you don't have the device tree segment, and so it cannot match. So the probe will not happen, and then you can overlay one segment of the device tree, adding it into the device tree or delete it from the device tree. And at that moment, the device and the device driver, these two parts will probe at this time. So yeah, and for FPGA device specifically, Linux also provides one infrastructure that is FPGA manager. It's very powerful. Yeah, but we will not dive into that. Yeah, and also another trick to decouple FPGA and Linux is in the designing time. One slogan, I think, I don't know what, one idea is every problem in software can always be solved by adding a middle layer. So just for example, I mean, there must be more solutions, but some easy to understand solution approach one is to add one hardware middle layer. For example, here PS is a terminology for processing system, the ARM core, and the PL is programmable logic, that is FPGA. They are in the same chip. They are in the same on the same SoC. So here you can use this part to provide some functionality like AXI smart connection, like AHB to APB bus, like a bridge, and use a resource on the PL like to do something like the random number generator because you will need it anyway, and you will need it, right? And it will not change. It will never change. So then the benefit is from the perspective of PS, the device tree or the peripheral devices attached to the ARM core has never changed. That's a benefit, and you can separate those functionalities, those applications or network protocol stack, anything that can or may change to separate FPGA devices. So that's one idea. You use a specific hardware as a middle layer. Another approach is to carefully design the FPGA architecture. Like you can separate those never changes or not likely to change as part of the blocks in the FPGA device, and isolate or cover or wrap those will change. Those FPGA functionalities will change to a separate place. So every time when you create the Linux, the Linux project, you only need to node this part, this persistent part, and node this volatile part dynamically at runtime. So that's also another approach. But the essence is to add some middle layer to cover the changing part. Okay. So if you're going to dynamically reconfigure the FPGA device, that will bring a problem of compatibility. For example, when we're talking about Wi-Fi protocol, it's a fake example. It's a fake example. I have application driver and the FPGA device, FPGA implementation. As you can see, the first version application would just want to use 802.11b. And the driver, the driver we write support BAG, and FPGA device actually support BAGN. So it's good. It's good. It works. And then application iterate, do a release, and also we adapted our driver, but FPGA is still working, and they found some big problems. They have to roll back, and now they only support BAG, but application is requiring B and G, so it also work, right? It also work. And V3, yeah, similar thing. It also work, but I want to see here. There is a lot of trade-off actually. What does it mean? Because if we wrote the driver supports BAGN and the FPGA device only support BAG, we have two choices. One choice is to refuse to node or refuse to match the device and device driver. Another choice that takes much more careful design is we can kind of modulate our functionality, right? We can modulate. We support B and G because I don't know. I don't know whether they are using the same frequency, and separate N, and now we can support. I mean, the device and the device driver can match parsney, right? And we can still match it. We can still use it, but we have some functionalities that we cannot provide. And how can we make this flexible between application driver and FPGA device? That takes a lot of careful design. But I just want to say compatibility is something we need to consider if you choose to dynamically node and probe the FPGA device. Okay, and regarding the implementation, when we really do our development, I think something we need to know for FPGA developers about for Linux developers about FPGA is that FPGA actually can be implemented as any device, so including storage, no matter it's volatile storage or persistent storage. So which means actually you can create a self-contained FPGA battery. Self-contained, that is, you can create a storage device inside the FPGA device, and that storage device can provide the hardware description information and any other information that you want. So I mean, the concept of self-contained. So and also one thing about FPGA, at least Linux, is we are operating on GUI, and as you can see, the TCL console is every operation. I click something, I run something on this GUI, there will be a relevant TCL command or TCL procedure underneath the water. So this TCL script or TCL procedure is flexible enough to add any hooks, to add any extra procedure that if you want. So for example, if you want to train if you want to train the block, the device tree, and you want to cover part of the design, you want to like because you know that part will change very fast, so you can just cover this part in this TCL tree, and also you can extract information and generate a JSON that provides the capability. For example, if here I can use this example. If FPGA version 2, they have a minor version which changed the 11N, and you don't want to iterate your device drivers version, and so maybe you can think about generate some kind of information inside the FPGA's storage area, and the driver or the application can use this information to know that this version of this release of FPGA changed something specific, or provide some specific capability. I need to handle it, something like that. So it's flexible. So go back to the target, or to the goal that we want when we want to decouple the FPGA and the Linux is some information questions that you can ask yourself about the dependencies. So if FPGA team add or remove or update one register, do we need to rebuild the Linux? Will the application or the device driver or the OS cannot reboot or crash or some application error? Will it happen? So if we change one device, not one register, what will happen? So in the CI environment is FPGA job and upstream of Linux job, and this is extremely catastrophe, extremely, because FPGA jobs normally takes a lot of time. And do we want to code reloading code reconfigure the FPGA device, or do we want to warm reloading the FPGA device? So the ideal scenario is thinking about how we use a USB Wi-Fi card. We just plug it in, right? We just plug it into it, plug in and plug out. Anything, nothing wrong, no crash, no application error, no rebuild of the PC's operating system like Windows or Linux. You will never expect you need to rebuild or reinstall the Windows, and when you need to plug in one USB stick. That's not possible. Of course, there is some difference because in this case, it's removing a slave device. It's not removing the controller device. But anyway, it's something that you can think about the ideal use case. And the last section is some extra information. I found one project that's quite interesting is PYNQ. I don't know how to pronounce, but this project is interesting because I provided a link. It's because it can partially reconfigure the device at runtime. So basically you have Python libs and Python libraries, Python modules, and you can implement the module in the form of circuits. And when you import the module, it will reconfigure part of the FPGA device, so you can use the Python module. It's quite interesting, and no matter regarding Linux infrastructure which are vital is no matter you are using what kind of solution, there are some things that are very helpful to know is device driver overlay technique and open firmware, and also FPGA manager. This one is relatively, I think it's relatively new. It's but it's useful. So just to conclude this this presentation is I'm not trying to sell FPGA solution. I just want to say sometimes it may be a better possibility if you have specific requirement regarding customized functionality or extreme performance, anything. And to use FPGA, we as Linux developers only need to know that we require the binary file and hardware description. That's what we need. And to use it, to utilize FPGA better and to save your life is you need to avoid or eliminate any unnecessary dependency. That's it. So that's this slide. Thank you.
Questions, anyone?
I have a question. One thing that concerned me when I was looking at FPGAs a couple of years ago was the lack of open source toolchains for them. Do you know if that has changed now? Are there open source toolchains available for FPGAs, and are they good if they exist?
Yeah, I actually, first of all, I'm not an expert regarding this. My perspective is FPGA is iterate. The production of FPGA is iterate very fast, and it has sometimes, or it's not sometimes, but many times, it has flaws inside the devices. So maybe it's better to use the tool chains from the vendors, even if the tool chain is sucks. I mean, take Xilinx as the example. The tool chain is very hard to use, and they don't promise any backward compatibility, but people are still using it, because if you're not using it, yeah, you can find some alternatives, but maybe more problems. That's just my personal view on this.
Okay, but so that means that the main tool chains are still closed source, then I take it?
Yeah.
Okay. All right, thanks, and thank you for the presentation. As someone who is not familiar at all to FPGAs, it was very interesting.
Okay, thank you.
Okay. Any other questions? Then thank you, Lou. And
thank you.
Everybody, see you in the next MindTech talk.
Thank you. Bye.
Bye.
Have a nice day. Bye.
Bye.
See you. Thank you, guys. Bye.